Hola a todos, mi nombre es Charlotte Wheeler y soy un investigador en la Universidad de Edimburgo y estudio la degradación forestal. Lo siento, pero mi español no es muy bueno, entonces creo que hablar en inglés. Espero está bien, pero mi presentación es en español. Okay. Okay, so just to give you an overview, I'm going to talk a little bit about the Forest 2020 project in Mexico, the types of degradation that we're looking at monitoring in Jalisco and Chiapas, the sites we're working in both of those states, and then I'm going to explain the methods we're using in this project to monitor degradation, and then give you some preliminary results from the Sierra del Tigre window area in Jalisco. Okay, so the main aim of the Forest 2020 project is to try and improve the use of satellite data in tropical countries, utilizing new satellite data to monitor the disturbances we're seeing in tropical forests. And my specific part within this project is looking at monitoring forest degradation. And so for this element of the project in Mexico, we're working with FIPRODEFO in Jalisco and AMBIO in Chiapas. We also have other partners on the project, so ProNatura Sur and Ecosur, but we're not quite so involved with them in this degradation element of the project. So in Jalisco, you know what, I'm going to change sides. I don't like it over there. In Jalisco, the main forms of degradation are fires. So here we have lots of forest fires and very burnt trees, and that's a big problem in these dry pine forests. They also have lots of problems with pests. You can see up here, or not so well with the colors, unfortunately, but here we have some trees, the brown trees, which are infected with pests, and they're causing quite high dieback of some of the pine species within these forests, and it's becoming quite a problem in Jalisco. And there's also problems with agro-industrial cultivation. So avocados, which is the avocado plantation here, is becoming quite common within this state. In El Ecote, so El Ecote is a reserve, a biosphere reserve in Chiapas. It has a lot of local communities living and farming within the reserve. So there is a lot of degradation happening within this area. So we have a lot of forest fires again. Some of these are intentionally set to clear land, but then there are also wildfires happening. Wood extraction for use within the communities is also common, and also for construction. There is some hunting. There's a lot of clearing for cattle ranching, and also expansion of agriculture. So here is some agricultural land. Some of the land there is actually quite poor quality. The soil is very thin and it's incredibly rocky, but some of the areas they're clearing for cultivation of crops such as maize and their staple crops are encroaching into the forest. Oh, sorry, too many. Our sites in Jalisco, so Jalisco is just here. We have 3 window areas in Jalisco. The coastal zone, Sierra del Manatlan, which is where we're visiting on our field trip tomorrow, and Sierra del Tigre. So at the moment we have some field data from Sierra del Tigre, so these are the points in green here, and we're going to be getting some plot data from the other 2 window areas soon. And then El Ecote in Chiapas, fortunately it's not very well, you can't really see it on the large map, but it's just down here. And we're working in 5 different communities in El Ecote. So this is just the southern part of the reserve that we'll be working in. And we're also trying to establish 10 plots within this reserve. So our definition of degradation that we're using within this project is looking at the loss of biomass from areas following anthropogenic disturbances in areas that are defined as forest and remain defined as forest following disturbance. So it's quite an important point to establish that degraded forest has a definition of forest at the beginning prior to the disturbance. Then once that disturbance has occurred, what we're left with is still standing forest. So that means that we're actually looking at gradual reductions in biomass a lot through time. And because of that, it's much more tricky to monitor than just normal deforestation, where we have just transition from one land use to another. And because our definition is looking at losses in biomass, we're wanting to use some metrics that can actually measure biomass within our monitoring. And for that reason, we're using radar data. So radar data has proven to be able to be used for monitoring biomass. So there's a strong correlation between the radar backscatter signal and biomass. So here is an example of that from a paper from 2009 in Africa. And it's in 4 different sites we're seeing similar relationships. So we know that this relationship is quite strong. But as you can see across the bottom, we have our biomass. And on our y-axis, we have our radar backscatter. And as biomass increases, our backscatter values increase. And here's the same graph, but on a log scale, so it's a little bit clearer to see. But as we can see, there's a clear relationship between biomass and this backscatter value. So we can use this as a proxy for mapping out areas and mapping out biomass within the locations that we're working in. Oh, sorry, this has moved around a bit. But our general methods are to download our radar data over our sites at time 1 and time 2, and collect field data at within these regions at time 1 and time 2. We're using the field data to calibrate the radar data. And then once we have the calibration, we can compare the 2 time points and see how the biomass is changing through time. So essentially we're looking at detecting changes in the backscatter from the radar. We calibrate that with the field data, and then we use that calibration to create maps of biomass. So in a little bit more detail, radar is very good, particularly in tropical forests, because it is able to penetrate the canopy of the forests, and it gives you information about the actual structure of the trees, rather than just giving you information about the physical, the canopy and what you're looking at. We're also, it's also not affected by cloud cover, which obviously within the tropics is very problematic. So because of the longer wavelengths, it doesn't interact with clouds, meaning that we don't have any problems in persistent clouded areas, which are very common across the tropics. So for this project, we're using ALOS Pulsar and ALOS Pulsar 2. So this is a double polarization satellite run by JAXA, the Japanese Space Agency. It's an L-band radar satellite, which means that it has a wavelength of more or less 15 to 30 centimeters. And that is the reason why it can penetrate through the canopy, because it's longer, the wavelength is larger than the leaves in the canopy, generally speaking. And then once we have collected and downloaded and done the pre-processing of our radar data in our window areas, we are calibrating that using our field data, which is permanent sample plots. So in this project, we developed a new protocol for establishing field plots to monitor degradation. So our criteria for our field plots are, ideally we need to have them larger, more or less about over 0.5 hectares in size. And this is because it's larger than a single pixel for the radar satellite. So for ALOS, the pixel is about 25 meters resolution. And particularly when we're using radar data, it's quite noisy. It has random noise built into the data, which is just how it comes, and it's quite normal. So we need to do some smoothing or aggregating of our data and averaging to make sure that we're getting accurate maps. So for that reason, it's better to have multiple pixels over a single plot rather than just a single pixel. And that's why we're encouraging the use of larger plots for the monitoring of degradation. We also need these plots to be situated in locations that are undergoing anthropogenic disturbances. So we need to be monitoring the areas that are undergoing change. And that allows us to capture these degradation events. And we also need repeat measurements of these plots. So as I said, degradation is a gradual process that is ongoing and is related to the loss of biomass. So we need to be monitoring plots regularly in the same place to see how these areas are changing on the ground. So for this project, we wrote a protocol for monitoring degradation and came up with this long, kind of narrow strip plot. With FIPRODEFO, we've amended the dimensions of the plot slightly, so it's 30 meters by 160 meters, which is just under half a hectare, and this is because it overlays with some of their old plots, which were 30 meters squared. But essentially, by having long, narrow plots, it reduces the time we need to spend in the field. We can start measuring the field plots at one end, establishing the subplots, and then we can just move up and along the plot, and as a group, we can remove all our tags and everything, can move forward, and hopefully we can measure a single plot in a day. And that's one of the important things for this project, is that we need to try and have a large number of plots, or as large a number of plots as possible, because obviously degradation is a very random process that is very hard to predict. So if we have a large number of plots, then it's likely that just a small percentage of those plots will actually be disturbed. So in order to actually capture this degradation signal from satellite data, we really need to try and install as many plots as possible and try and do that relatively rapidly. So, and also we're trying not to put any marks on any of these plots so they don't visually look like they're being worked in. So the behavior of the people that work and move around these forests is not affected by the presence of any scientific research. So this is just the beginning of the results then. So this map is Sierra del Tigre, and it shows you the radar backscatter. I think the word retrodispersión is correct, but it's a bit of an unusual word in English as well, so we'll hope that it works. But essentially this map here shows you the HV backscatter values across Sierra del Tigre. The darker values here are associated with the lower value backscatter values, and the lighter areas are associated with the much lower values. And essentially these light areas are agricultural lands, and the dark areas are the areas that are forested. So the darker the area, we should have higher biomass forests. So once we got our plot data for this window area, we conducted a regression analysis. So we have 10 plots in the, well, all these red points are the plots. So we have 10 plots in the Sierra del Tigre window area. And we performed regression analysis looking at the biomass and the backscatter values for each of these plots. So on the x-axis here, we have our above ground biomass, calculated using the Chave equation, which someone else mentioned earlier, and that's plotted against the backscatter values. And we essentially perform a regression to see what the relationship is between these two variables. We fit various different lines, so both linear and non-linear regression equations, to see what the best relationship is. In this case, because we only have 10 plots, there is a linear relationship, which is continually increasing. But in actual fact, normally it's non-linear. So in the graphs I showed you earlier, you could see there was quite a sharp curve at higher values of biomass. But because we only have a smaller number of plots, those sort of more subtle changes are not quite so easy to see. But essentially, we now have a regression equation that is related to this change for this particular region, and we can use that to calibrate our maps. So When we're actually building our map, there are certain things we need to consider. So the backscatter signal does saturate at higher biomass values, so about 150 tons per hectare. So as you can see here, our highest plots are just over 150 tons, which is actually ideal because it's not going into that saturation point. But essentially, we need to eliminate pixels that are higher than this value, as these are high biomass forests where we can't really rely on the signal, the backscatter signal, to be giving us clear information about biomass. We also need to eliminate areas with very low pixel values that are associated with agricultural zones. And obviously, for this project, we're primarily interested in the forested areas, so we want to remove the areas that are under permanent agriculture. And then using the regression equation we've developed, we can use that to calibrate our biomass maps. So here is our first sort of biomass map for the Sierra del Tigre area. So the green areas are sort of the high biomass plots, and the brown areas are associated with agricultural areas. So this is just a sort of first run of the biomass maps for this region, and it still needs quite a lot of work. But it's just to give you an example of how this information can be used to produce biomass maps of the areas we're working in. And obviously this is a single biomass map, so it's more at this point a baseline for our work going forward. What we're particularly interested in more so is the actual change in biomass from one time to the next. And unfortunately, it does say biomass in 2016, and our plot data was collected in 2017, but fortunately, ALOS don't release their free satellite data until around about this time each year. So hopefully in the next couple of weeks, we'll get the 2017 data and we can update our maps and use the correct time points for when the plot data was actually collected. But essentially, this gives you an idea of what we're doing. But moving forward, we obviously need to do some error checking on this map. We've used some fairly simple ways of masking out the high and low values of backscatter, which maybe aren't the most accurate ways of doing things, but it was more to kind of show everybody while we're at this at this workshop. Been doing this analysis until very recently, so it still does need some work. We also, in this sense, we use the limits of the regression equation to mask out areas, but also we can use training data and polygon data that is available locally to help improve the masking. So for example, if we have polygons showing areas of permanent agriculture or polygons of areas that are intact forests or in protected areas, then that can really help us improve the errors we see within our maps. We also are going to be including in Jalisco, the Sierra del Manatlan and the coastal region, doing the same analysis for each of the 3 window areas. So I think the plot data is still sort of being collected at the moment. And once we have that data, we can create these maps for all 3 regions. And similarly, we'll be doing the same analysis in El Ocote in Chiapas once our field data is being collected there as well. And also, this is our baseline year, our first year of collecting field data. So moving forward, we'll need to be remeasuring these plots on an annual or biannual basis to see what is changing. So hopefully that means we can create biomass maps from our baseline year, which would be 2017 when the project started, and then moving into the end of 2018 and looking at the actual change that's occurring within our different regions. Thank you. That's just an overview of what we're doing. I think it was a bit shorter than 30 minutes, but any questions, please?
Bueno, damos un aplauso a la doctora Charlotte, por favor. Y entramos a la sesión de preguntas. Aquí tenemos una con la doctora Margaret. ¿Sí? ¿Quién más tiene otra pregunta? Por acá atrás. ¿Alguien tiene algún? Bueno, empezamos con la doctora Margaret.
Okay, just an information question. Roughly how big are those windows that you're using? How many square kilometers, roughly?
Posible es una pregunta para Gaby.
Okay. Okay.
Más o menos como
¿Cuántos?
150,000 hectáreas
Yeah.
de las 3 áreas ventana. Las 3 áreas ventana, lo que buscábamos, como son estudios preliminares, es tratar de abarcar la mayor cantidad de ecosistemas que están representados en los bosques de Jalisco, por eso y que además presentan distintas problemáticas. Está la parte de la costa pegado a Chamela, y bueno, y buscando correlacionar donde hay áreas naturales protegidas y donde no hay.
Yeah.
Entonces, la área ventana que está en la costa de Jalisco está muy pegada a Chamela Cuizmala. No ha habido tanta apertura de la UNAM como quisiéramos, como es el caso en Sierra de Manantlán, por ejemplo, que hay una participación muy cercana con la dirección de la reserva. Se tomó la reserva de la biosfera, la mayor cantidad, hacia la zona donde hay mayor aprovechamiento y manejo forestal, que es el lado de Cusalapa, sí, Ayotitlán, sí, y toda esta zona. Y en Sierra de Quila, que es una parte de una de las cuencas de abasto identificadas por la CONAFOR, pero que también hay una dinámica de cambio, sobre todo por la presión de la agroindustria, en este caso del aguacate y de la de berries, principalmente aguacate porque es la que compite con los bosques. Entonces, buscando combinar estos aspectos de impacto socioeconómico, que está esta dinámica económica ahí, ver cómo se puede correlacionar ya después con la propia ecología y dinámica de los bosques. Y entonces el tema de la degradación para nosotros sí es muy importante por lo que ya les había comentado, ¿no? Ese es como...
Thank you. Thank you for the clarification. But I mean, my point is that you've got 10 plots only in those quite large areas. And I understand the reason for the size of the plots. But are you then doing the radar analysis for the whole window or only just for the plots? And I mean, because you could do some smoothing, you could do all kinds of interesting analysis.
Well, the mapping that we've done is for the whole window area, and it's calibrated from those 10 plots.
Okay.
So, I mean, obviously with more plot data, we can improve the accuracy of our calibration, but at the moment we just have those 10 plots. But they cover, I mean, one of the good things actually, which I didn't really mention, was that our plot data does span a wide range of biomass values, and that's really important because we can actually develop that regression equation. If all of our plots were sort of around the same point, it'd be very difficult to actually put a regression line through that. So having the plots covering...
That was my last question. Did you deliberately select the plots to represent that range of biomass?
Well, actually, for this area, the plots were mainly selected by Gabby and Hugo, and they're old plots that FIPRODEFO already had in place. So in the they basically have these 30-meter square plots that we overlaid and we've extended up. So we actually have more data for this point down here, which may be useful in looking at some processes of growth increments and things like that, or changes in species turnover and mortality, but potentially at a more local level. But I mean, obviously, it's all dependent on the balance between time and money and, the number of plots we could fit in. So. Sí, lo que pasa es que FIPRODEFO tiene lo que se llamó, porque ya es viejito, salió un poquito antes que el inventario nacional, es un inventario de recursos naturales. Ese inventario de recursos naturales, evidentemente la metodología ya quedó rebasada porque fue un proyecto ya tiene casi 16 años. Entonces lo que nosotros buscamos, como para dar una idea de un tiempo cero, es modificar un poquito la metodología de Charlotte y poner en medio ese punto central que más o menos abarca 30 metros. Entonces, todas las parcelas tienen un punto, están enclavadas en el punto de monitoreo que tuvo el FIPRODEFO en ese momento, para ver qué había en ese momento, qué hay ahora y poder intuir. Pero obviamente no abarcan, pues esto es casi media hectárea, ¿no? Y aparte tiene una lógica rectangular, el otro son círculos, ¿no?
bueno, un píxel de lanza, más o menos.
Sí. Por favor.
Marcela se llama la colega? Gabriela. What just Gabriela said brings me something to my attention, that is this one. It doesn't really matter the shape of the plot to do this kind of analysis. I mean, from the the data from the sensor to the biomass, I think that's a great opportunity to recover part of this data and try to include it here, and I will try that. I mean, just to increase the sample size. And not only that, you have a very great opportunity to use some ratio estimators, sampling ratio estimators, to get the whole biomass over there, because the relation is pretty linear, at least in this area. I mean, I won't discard the use of older data in this case. Not at all.
Yeah, essentially the shape shouldn't matter so much as the size. We're choosing rectangular plots because obviously with circular plots it's a lot more difficult to mark out the edges, and to get a really good location for the calibration, it's really good to have corners. And also because the pixels are square, I mean, sometimes it just helps. But I mean, circular plots can be fine, but obviously you just have to make sure your circular plots are large enough that they cover multiple pixels again. And maybe instead of, I mean, a lot of the circular plots I've seen, they just have a single GPS location for the center and no marks on the edges. And sometimes it's just nice to have even 4 points on the edges of a circular plot just to constrain your location a little bit more.
Okay. Muchas gracias, Charlotte. Tengo una pregunta y un comentario. Primero, bueno, mi inglés creo que es un poco limitado. No sé si explicaste el método de interpolación para crear el mapa. Tengo entendido que a partir de las parcelas que tú tenías, hiciste la regresión, y con esa regresión tú hacías la interpolación de cada uno del contenido de carbono que tiene tu mapa, ¿cierto?
Sorry, I couldn't hear very well. What was that?
La generación de tu mapa
Sí.
fue a partir de la ecuación de regresión que tú sacaste con tus mediciones de parcela, que fueron 10 parcelas. 10 plots for created the map.
Solo es un análisis de regresión lineal.
Ah, ok.
Pero yo ponen otros tipos de línea de regresión, non lineal, como...
Ah, ok. Bueno, en ese sentido también va mi comentario. Posiblemente podrías mejorar una predicción o una interpolación teniendo otra capa con mayor cantidad de datos. Es decir, identificar alguna variable que te pueda explicar un poco ese contenido de carbono, que tenga mucho mayor datos para crear una interpolación geoestadística que te representara un poco más esta curva que no es totalmente lineal. Es solamente una sugerencia. Si quieres lo platicamos.
Well, the analysis was done in R, and we literally just plot the data of biomass and backscatter, and you just can fit. And because R is very flexible, you can just fit different lines and write the equations yourself, and just then do some simple modeling to see what the best line of best fit is, essentially. I mean, it's a basic kind of linear and then non-linear regression to see which relationship fits your data best. I mean, typically we have a asymptotic function.
Yes.
So similar to this, where it's increasing and then flattening at the top. But we don't have enough plot data really to be able to see that, which is why for this analysis, I use this equation, and for any plots with a value, a backscatter value that corresponded with 150 tons, I just masked out and said that they're high biomass pixels, and so we can't be sure of their actual real biomass, which isn't necessarily the best way to do it. It's a bit of a quick quick quick
Thank you very
method,
much.
but just
Okay.
for kind of demonstration purposes, that's how I did it with this. But yeah.
Una pregunta más.
Hi, thank you very much for your presentation. I have a small question for you. Do you have any validation strategy or something to compare the values of biomass? Because probably if you have 10 plots, you can capture the domain of the actual values that biomass is in the area of in the study area.
You mean validation of the plot data?
If you have something to compare the values that you found in the field.
I mean, we're using just standardized allometrics to measure biomass in the field, which are, pantropical allometric relationships, which are fairly standard protocol. So I'm fairly confident that the biomass values we're getting are going to be okay on the ground. I mean, there's errors within any allometric relationship, but we use the the recent CHARV equation from 2014, and that's being very widely used across the tropics. So while there may be errors inbuilt within that, they're similar to errors that other papers and other research will be seeing because it's the same equation. So I think in the end it'll probably balance out. Like a lot of the papers that the work is developed from have used those equations to estimate the biomass on the ground as well, or the predecessor from the earlier CHARV paper in 2005.
Okay, thank you.
Bueno, pues bueno, muchas gracias entonces a la doctora Charlotte por esta presentación. Nuevamente otro aplauso para ella.